Let's use the definition of the derivative to get the slope at any point along a curve. And the curve I want to work with today is the parabola y equals x squared. So there it is, and it continues off forever. So we're working with this function today. And the point whose slope I'm interested in, I'm going to pick the point at x equals 5. So it's a point right there, and the y-coordinate at that location is 25. The axes aren't to scale, but that's not important. And the way we're going to get the slope right there, because the slope's always changing, is choose a second point further away. And I'm going to mark it up there. And it's actually h units away horizontally. And h right now could be 2 or 3 or 4, but we're going to make h shrink to 0. And as h shrinks to 0, it's going to move that second point closer and closer to the first point, and we'll get a better and better estimate of the true slope at x equals 5. So here's how we're going to do that. The definition of the derivative at x equals 5 is a limit. And that limit is going to occur as h gets closer and closer to 0. And we're going to get the y value at this location minus the y value at that location, and that will turn out to be f of 5 plus h minus f of 5. And then we're going to divide by the change in x right here, and that change in x is h. And we're going to try to evaluate this thing algebraically. One thing to notice, though, I'll move it up a little bit, is that if we try direct substitution right now, if we try putting in 0 for h, we're going to get f of 5, which is 25, minus f of 5, which is also 25, divided by 0. So we're going to get 0 over 0. That's not a useful result, but it actually holds great possibility. So let's see what we do when we explore this algebraically. I'll get out my pen again, and I'll move this down a little bit more. And we're going to get now, again, the limit as h goes to 0. It's going to feel tedious to write that over and over again, but it's nice confirmation that f prime of 5 is actually a limit. Alright, so f of 5 plus h, we're working with the parabola x squared, so f of 5 plus h is 5 plus h quantity squared, minus f of 5, 5 squared is 25, divided by h. Alright, let's expand that expression and see where it leads us. So again, we're going to take the limit as h goes to 0. If I expand that, I get 25 plus 10h plus h squared minus 25 all over h. I'm going to pull out another color pen because I want to do a little canceling now. The 25 at the start cancels with a minus 25 at the end. You also might notice that there's an h in this term, there's an h in that term. Let's factor out an h. So we get the limit as h goes to 0 of h times 10 plus h over h. And what's great about this result is that we can do some canceling. I guess I'll have to cancel in a different color. These h's go, and the reason why they go is because they're forming a hole in the graph. If we were to take this expression with the h's in it, we would get a picture of a line. We would get the line 10 plus h, but it would have a hole in it at h equals 0 because of those two factors. By canceling them, we remove the hole, and now we are able to evaluate the limit. And it's the limit as h goes to 0 of 10 plus h, which equals 10. What we've just figured out is that the slope at 5 on the parabola x squared is 10. So I'm going to get my picture back on the screen, and I'm going to pull out a new color. And the function right here, right at x equals 5, if we were to zoom in a lot, it would look like a line. And the line it would look like would resemble something like this. It's not a very straight line, but I think you get the idea. And the slope of that line is 10. And that line is called the tangent line. It doesn't cut through the curve at all, as it would if we were using two separate points, like these 2 points. It's a tangent line. It just touches the curve, and it has a slope of 10. And it's modeling the slope right at x equals 5. It took mathematicians a long, long time to make sense of the concept of limits and to work algebraically to arrive at this result. But I want to extend it a little further now. We're going to go down to the bottom of the page, and rather than work at x equals 5, let's work at a generic location, at any location. So let's see if we can repeat what we've just done, but work at a generic location x. And this is the formal definition of the derivative. It's a limit as the change in y over the change in x goes to 0. And let's see if we can work with this in the particular case of a parabola. So, f of x plus h is x plus h quantity squared. F of x is x squared over h. Just like before, we can expand the numerator, and we get x squared plus 2xh plus h squared minus x squared all over h. You're probably already anticipating what I'm going to do next. And that is I'm going to cancel these x squareds. That will always happen. Your beginning and your end terms will cancel. And the other thing you probably know I'm going to do, factor out an h out of those two terms. So let's do that. And we get a limit as h goes to 0 of h times 2x plus h over h. And I'll pull out a different color to cancel. Remove the hole in the graph, and then we can rewrite our solution. When you put in 0 for h here, you just get 2x. So what we've seen here is that on the parabola x squared, the slopes behave according to the function 2x. So if we want the slope at any location on the curve, say at x equals 20, the slope would be 40. Say at x equals negative 9, the slope would be negative 18. And it saves us an awful lot of work. We don't have to go through the headache now of evaluating the limit in the formal definition sense for every point on the curve. Now, you've also seen in earlier math classes that on a cubic, the derivative follows this behavior. And if you work with a fourth degree function, the derivatives behave according to a cubic. And in general, if x is raised to any power n, the derivative is nx to the n minus 1. And that works whether x is, x can be any point, but it works whether n is a whole number, a fraction, a negative number, a decimal. This is a very versatile rule, and it's the power rule. And what we're going to do in class is prove why it works. And the way we're going to prove why it works is using Pascal's triangle.